welcome to the first Func Prog Sweden this year. We're super thrilled that we are finally back and we're getting started. Before we kick off this first meetup, I would like to recap the last year. We actually did 11 online meetups last year and we had 24 presentations in these 11 meetups. And amazingly enough, people have watched over 8,000 hours of functional programming in this channel. So with that, I would like to say and thanks to all viewers, watchers, to presenters. Thanks for coming and supporting us. Thanks for sharing and joining in today also. With that said, let's get started with the agenda. So first it's me, of course, Magnus. I'm doing introduction, etc. Then we'll hand over to Ben, and he will do Purescript for Haskellers. And after that, we'll do Orthotope. I think I got it right, or not. Apple-inspired arrays for Haskell by Lennart Augustsson. And then in the end, we'll do a schedule and a summary for this year. First up, I would like to thank Adabeat as our video sponsor for this first meetup. Adabeat is IT consulting as a company where most of the developers have a background in functional programming. Adabeat is based in Stockholm but have recently also opened an office in Ho Chi Minh in Vietnam, spreading functional programming there also. If you want to support the community, please join the meetup group over at MeetUp. Follow us here on YouTube and subscribe. And also check out the store, Func Prog Sweden, myspreadshop.net, where you can get a cool t-shirt like I'm having with the meetup logo on. Yeah. If you have questions during the presentation, please use the chat. I will read it up or the presenter will see it and will interrupt so you can get answers to your questions. With that said, let's get started. First presentation. Ben. Welcome, Ben.
Hey there.
Hey, welcome.
Thanks for having me.
Yeah, you're warm welcome. You're coming from us all the way from Toronto.
I am.
Yeah.
Yes.
Really cool.
So I suppose I'll just jump in.
Do it.
So thank you for coming to Purescript for Haskellers here at Functional Programming Sweden. My name is Ben Hart. I'm the director of Cardano operations at mlabs.city. So mlabs is a Haskell and Rust consultancy focused on blockchain as well as traditional finance. We are hiring like crazy. So if you are someone who knows quite a bit about Haskell or Rust or Purescript, we're very interested to talk to you. I'm going to drop just a link to our Haskell job posting in the chat. But if you have questions, if you'd like to get in touch, we're happy to have a chat. And if you're interested in maybe moving from a hobbyist role in Haskell to a full-time position, that's absolutely on the table. Come have a chat. Come engage with myself or our hiring managers. We're happy to have a chat with you. I am Canadian, so disregard any extra U's you see. I've been doing Haskell and Purescript. I learned them simultaneously about 4 years ago. I come from a functional full-stack JS perspective, and I really strongly believe in simple Haskell as sort of at least the first line of attack on a given problem. So what are we doing today? I'm going to do a brief introduction to the Purescript language design and its origins. I'm going to live code a project setup, a hello world, and then we're going to do some DOM manipulation, FFI to JavaScript, and some opaque types work as well. You're welcome to follow along. It's set up in such a way that you might be able to. On the other hand, if you're more happy just watching and asking questions as you go, that's just fine too. All right. So JavaScript, this might be controversial, is actually pretty great at times. It does run anywhere. it seems to be all okay at doing its job without nicks. It's one of the best funded interpreters on Earth. There's so much money that goes into just making JavaScript more and more efficient over time. It does have first-class functions, even though it doesn't have a type system. It's an incredibly well-maintained ecosystem for a ton of common tasks. So NPM, for all of its faults, at least if you're looking to get a job done, there's usually a package that can help you, and it might even do it, reasonably correctly. It does work on the front and back end, and it has this really convenient thing for web integrations in particular, which is anonymous records. It has anonymous objects without a particular type. JavaScript is also terrible. I think this is less controversial. There's no types. There's not a lot of correctness guarantees when you write a function. You don't have monads unless you're working in sort of a particular subculture of libraries, but they're pretty good, the ones that exist. I really, really like Sanctuary.js and Ramda, and they actually all come from a bunch of Haskellers who were working in JavaScript and saw potential for something better right around the time that the JavaScript promise was released. It's a really interesting read if you want to go take a look at those threads. Major refactors are pretty hopeless in JavaScript because you can only get type errors at runtime. And it does have something like 4 or 5 different types of null. Haskell, on the other hand, I think this is pretty uncontroversial, at least in this crowd, is it's pretty great. We have all of the types and functions we could really ask for unless we want to reach out to Idris and get dependent types. You have all kinds of abstractions with correctness guarantees. It's probably got the most advanced testing ecosystem out there, and you do get provable behavior out of your programs. But Haskell has some pretty terrible aspects. There's multiple types of string. The list is available in Prelude, and it has performance issues. It has some unreliable maintenance on vital libraries. There can be a level where you're doing type level work and very few people can maintain it, even among experienced Haskellers. You end up in this world where everybody's using a slightly different version between all of the different pragmas that you can enable. I would say there's build system issues just in general, and there's a lot of sort of unsafe functions in base that mean we just can't have nice things. So there's a ton of issues with Haskell, and there's what I would call is it's really cruft. It's things that we're married to mostly for backwards compatibility, and if we could do it all again, we would probably do it just a little bit differently. So I think there's some synergies here. Purescript attempts to provide a type-safe Haskell-like language. It has type classes, it has most of the features of Haskell, and it compiles down to high compatibility JavaScript. So it actually compiles down to JS version 3, if I recall. So you can use simple FFI bindings and row types, as you'll see, to sort of get into anonymous records and start to build up a more natural way to program in both front and back end web. Purescript is generally more demanding of its users, though. It's more polymorphic, for example. So from foldable is used for collections rather than from list. And this can create some real problems because your compiler has less information sometimes. So this means that things like type tools are a little bit less useful than they would be in Haskell. But we don't have any pragmas. That means the compiler is much easier to maintain. And in fact, it is maintained by a far smaller group of people than GHC is. It's got its default head function actually returns a maybe. And in fact, the whole language is sort of taking a page from Idris. It's total by default. Now, if you need to introduce a partial function for, say, a partial pattern match, you can do it. The compiler will catch you, and you have to add this partial type class to your function to make it possible. You do have JSON and foreign parsing to get up from sort of untrusted JavaScript types into trusted PureScript types. Hating algebra is interesting. So hating algebra is just an abstraction over Booleans, really. I mean, you can be more abstract about it, but this is a good example where It's more about things that are Boolean-like. So these can be maybe bools or functions that return a bool, and you can get the composition that you're looking for using or and then these simple methods that you would usually just use monomorphically on Booleans. So you get row types and anonymous records, and this is kind of what that looks like. So we have dot access, very similar to the dot preprocessor, but your type here is actually some record which contains a property named prop at the type of A, and then you can get your A out. This means there's other rows. So this is a row type. It's and it will accept an anonymous record or any record that would fit this shape. Records are a standalone type in Purescript. So if you want a new type over a record, the constructor just takes sort of the whole record as an argument. Okay. And you have FFI and native Purescript function frameworks as well. So you can use something like Halogen, which is entirely written in Purescript using free monads, and you get all of the type safety. It's an incredibly type safe library. Or if you want to opt for something like React, there's absolutely multiple versions of React bindings available in Purescript. And I will say in general that the entire ecosystem is really geared for production. More improvements. Well, you can have symbolic inline functions just like you might have in Haskell, but they require a name. So you're not stuck with everybody trying to understand how to pronounce a certain symbol. And I think it makes understanding and reading code much easier. Linting is built into the compiler, so there's a lot more warnings that give you recommendations. In particular, I'm a really, really big fan of what they do with imports, where you can have one unqualified import. Usually it's your prelude. You don't get implicit prelude, by the way. You manually say what prelude you want to use. And then everything else is either brought in under a qualifier or as just named imports. So it's very, very explicit about what's happening in the module and where everything comes from if you follow those linting rules. You do also get generic implementations for free out of a ton of type classes, including show. So the compiler will derive generic for you for almost anything that you can think of. And then you can go ahead and use sort of generic show implementations or generic implementations of almost any type class you would look for. And since we're using sort of the underlying JavaScript representation as generic, it's a little bit more performant, certainly at compile time, than you will ever see from the GHC generic as well. Maybe a little bit closer to like generics SOP. There's also this function in the debug library called spy, which is really handy because it lets you see things that aren't showable. So it's really great for debugging. And you can also have flexible backends, so you're not limited to JavaScript. Purescript works directly by working, it can compile down into things like C++ or C directly. And so you could theoretically build up a set of packages for compiling Purescript to WASM, for example. You do get some compromises in Purescript. It's not super performant when wiring up JavaScript libraries. If you're doing a lot of work in Purescript, that code will run a little bit slower than if you wrote it in bare JavaScript or TypeScript. Your footguns are with the FFI. Those types are trusted. There's sort of a handshake when you do the foreign function interface. With JavaScript, you have to make sure your type is accurate. Sometimes you could have the wrong underlying type. Purescript is going to trust it. It is strictly evaluated, but writer doesn't have a space leak. Compilations, they roll in your dependencies so that you can actually cause excessive bundle sizes, and you'll have to go and minimize your work afterwards. And there are some unmained tools, and I'm pointing here directly to Purescript Bridge. It's not maintained. There's a billion forks of it. Find a good fork, though, because it's really, really powerful. It lets you take Haskell types and share them with a Purescript library, essentially. So it'll generate a Purescript module with all of your Haskell types and correspondingly equivalent encoding and decoding for Java, JSON, for example. But your type tools are, as I mentioned before, a little bit less informative than you would see in GHC. So you get some familiar friends out of the box. We get Pursuit, which I'll flip over to. Pursuit is an awful lot like Google, and you can see it's got a ton of packages. It's a really mature library of packages, I think. Lots of wrappers for common JavaScript libraries, as well as re-implementations of a lot of friends that you would be looking for in Haskell. So your list and set implementations, they're all here, and they actually have pretty good performance properties for those data structures as well. All right. You can easily pull in an NPM library as well and wrap it if you want, if you're confident with that library. You get Spago, which works a bit like Stack, so it manages packages and sets that are known to be compatible with each other. You do get PSCID and PSCIDE, which are tools for interacting with the code itself and getting rapid iteration. You do have a quick check port as well. You get a dedicated team of maintainers who really care about production usage. And instead of IO, you get this sort of effect and AF monad. So these are synchronous and asynchronous effects, respectively. So in one, for asynchronicity, you would use like continuation passing, callbacks. And in the other, you'll have something more like IO in Haskell. Yeah. And it's easy to go from one to the other. All right, so at this point, I'm going to jump into actually doing some live coding, but I'd like to take a moment if there's any questions. I don't see any in the chat. Do we take verbal questions? I'm not sure.
No, we don't.
All right.
I don't
fine.
see any questions, and I
great.
don't have any questions. No.
All right, so we're going to jump in and actually start a project then. Yeah. I have already gone ahead and installed Node and NPM, but I really recommend this tool if you're not used to working with Node, to use the Node version manager, at least until maybe if you're a Nix expert, you want to go and get it set up in Nix, or if you're using Nix OS, this might be a bit of a blocker. But I would recommend, if you're not going to use Nix and only Nix, go ahead and use the Node version manager. I recommend this one. I believe it's the current LTS version of Node. Then you'll want to install Purescript itself, Purescript PSA, which makes the error messages slightly better, and Spago. And I really recommend PSCID, especially if you like the GHCID. They're really meant to be very similar applications. Okay, so I'm just going to switch over to my sort of coding workspace, and we're going to see just sort of setting up a project and getting to a basic hello world, and then we're going to move into a browser. Okay, so I'm going to just make, we'll call this like my project. Okay, so we're in an empty directory, and we can just do Spago init. And I will show you what that looks like. I'll just get a second terminal up. Okay, so we have a spago.dal. This defines the dependencies for your package and gives some additional information about how your package should be built by Spago. Okay. Then you have the packages.dal, and packages.dal defines your package set. So here we're actually linking to an upstream package set, and we can add in overrides and additions to that package set as well. So if you want a particular version of a package or a package that's unlisted, you can specify that all in DAL. So the whole ecosystem is really geared around DAL-based configuration. So we have a main.pers, and it has an effect function similar to IO, and it's going to log out a bowl of spaghetti. So we can do spago build. And after some compilation, we get a successful build. Spago run, we'll just always run main.main. And we get our little bowl of spaghetti down here in the corner. All right, so at this point, we've got a really basic sort of hello world. But what we want to do is we'd like this to run in the browser. So what I'm going to do is I'm just going to guide the next couple steps where we actually walk through getting this set up in the browser. So we've already passed everything here. You can also do like to run tests, you can have spago run main, and then you specify your main functions. Here we go. So we're going to do a hello world in the browser. And the first thing that you'll want to do is grab some boilerplate that's in the spago docs. So I'm just going to say like, GitHub spago. Just go grab that. And you'll even see they have sort of in their table of contents, they'll talk about the super easy, super quick tutorial. And then down a little ways, they'll say, okay, I want to set up a project into a single JS file, or we want to set up like a browser or node based project. So upgrade package set. Oh, make a project with Purescript and JavaScript. Here's what we want. And I would really recommend Parcel. There is also some settings for Webpack, but Webpack is a much, much more complex build tool. Parcel will definitely get you up and going, and it is just fine even for some large projects. So we've got the super quick tutorial down. We can initialize a JavaScript project. And so you'll see we get this sort of situation where we have two layers of build system. So we'll do npm init as well. Package is my project. There's a few things npm wants to know. I'll just kind of skip those. Yes. And we have our, I'll just kind of renew it up here as well. Package.json added. Okay. Flipping back, the next step is we're going to install Parcel. And it's good to do it as a development time dependency. So Parcel's going to download. So Parcel is a bundler. It's going to take our compiled output from Spago, from the Purescript compiler, and it's going to bundle it up with some JavaScript target so that it can be incorporated, say a bunch of different JavaScript modules as sort of a single JavaScript module that we can tie up to a web page. While that is coming in, we are going to add two files. One is a main.js or an index.js, and the other is just a piece of HTML. I'll grab the HTML first here. Okay, this is going to be index.html. And we will also grab this. So all this piece of JavaScript does at this point is it imports from our output folder our main module and then calls the main function. That's all it does. And this will be index.js. Helps if I actually copy it. There we go. Okay. So the next thing that we'll want to do once we have these is we just want to add a extra script to our package.json. For those of you who might be new to sort of the NPM ecosystem, this works a little bit like a makefile, you might say. So here we're defining scripts, and the nice thing about them is they are scoped to include our specific dependencies. So some people might not just use Parcel for this. They might also actually bundle the precise version of their Purescript compiler here in your NPM package so that it's giving you the correct versions everywhere. You can also build up a makefile, of course. That's fine too. That's better if you're using like Nix, I think. Okay, so here we should be able to say npm run dev. Couldn't read, get report of undefined. You know what I think this is? I think this is actually I can see that my node version has regressed. So I'm just going to say nvm use 14.17.3 to get onto the correct version. That should be just fine. Yeah, there we go. So Parcel is going to put that up at localhost 1234. And Parcel, you can see here, is pointed directly at our index.html. So it sort of recursively sees, oh, there's a JavaScript dependency. It pulls in index.js. And then it sees index.js pulling in all of our output files. So it bundles those up for us too. Heading back over to our browser, we should be able to now visit our page. And we're not doing any HTML yet. It's an empty page, but we should be able to see our app actually started. So starting app, that's from our boilerplate index.js. And then here's our little piece of spaghetti. So we've now got a Purescript project working in the browser. And we're able now to start interacting with browser APIs. And so that's sort of the next step here. We could easily change the spaghetti to hello world, and we would have hello world. One nice thing about Parcel actually is, and I'll maybe get this running. Now that I've got it, I'm just going to send that off to another workspace in Linux, and I'll set up a new terminal. So what I can do now is I can run pscid, and I can start to make live changes, and they should be reflected in my web page. So it's all hot reloading. Let's come here. So we can do that. We can say, all right, I don't want spaghetti anymore. I want hello world. So you can see that responded automatically, and I'm pretty sure our bundler would have reloaded. Let's go take a look. Yeah, now it says hello world. So that is how we get hot reloading in the browser from Purescript, which is just a tremendous way to get more productive when you're doing front-end work, I find. Okay, so the next step here is we're going to actually start implementing some DOM manipulation. I don't seeing any questions in the chat, so I'm going to assume we're going to hold off on any questions until the end. So we're going to jump straight into DOM manipulation. So for those of you who are new to working in the browser, DOM stands for Document Object Model, and what we're talking about when we mean DOM manipulation, we're just going to put something on the page, and in this case, we're going to use a div element. So I'm going to assume that there's some general familiarity with HTML. So the DOM manipulation would be anything that you can do to interact with HTML at runtime, inserting objects into it, removing them, anything that applies there. So we're going to use FFI to do this. I'm not going to bring in a dependency that already does it. We're going to use native browser APIs. So we kind of are going to want to work with some kind of an HTML type. We could build up complex types where we know the internals, but what I find is a quite useful technique to get started and sometimes to go right to production is to use an opaque type. So we're going to talk about some HTML. We're not going to provide a constructor, but what we're going to provide are some JavaScript functions that return some HTML, and that's going to be our type. That the only way to get it is sort of through JavaScript smart construction. So let's talk about sort of the first thing that we want ultimately is sort of a foreign import of, let's call it like append string to document. Okay, and we can decompose this a bit, but let's just say we want to put a string onto the document. So maybe what we want is string to effect HTML, and it is an effect simply because it's going to allocate memory, even if we're not attaching it to the document itself or we're not putting it on the page. There's an allocation of memory to go get this this node that is it's sort of existing in the page, and it can cause a memory leak if you don't get rid of it. So it's a good idea to actually have an effect for, I would say, most of your JavaScript functions. The other thing is you might throw an error, and I think that's part of the contract here when you're dealing with FFI, especially DOM manipulation. Your DOM manipulation can fail. You could supply some kind of invalid string, perhaps. So these are the reasons why we're going to label this as an effect. So again, sort of analogous to I/O. Let's see, the foreign module implementation is missing. Well, that makes sense. We haven't made one. So Purescript looks for a foreign module just to have the same name as the Purescript module that imports it. So in this case, we want like a main.js. Okay, so we have a main.js file now. What do we want to put here? Well, we want this sort of exports. I'm just gonna bring this down a few lines so it's probably easier to see. But exports dot, let's see, what did we call that? Append string to document. There it is. And let's see, we're going to use arrow functions in JavaScript here. So all we're going to do is we're going to take a string, and in effect, in Purescript, there's no wrapper or anything. It's just a function that takes no argument. And now we have, so this is currying in arrow functions. And now we can actually start a function body. Okay. So if you're used to sort of an older JavaScript syntax, you might have used like the function keyword. So it would be a function that in turn returns another function that takes a unit or an empty set of parentheses here. And then we're finally getting into the active part of the function. We've gotten past any currying. Okay, now this is going to take a string. So the first part of this is we'll need like something from window.document.create text node. And if you're wondering where to get resources on this, I really recommend MDN is a really great resource for any browser API. I am working sort of directly from this JavaScript manipulation tutorial from Tutorial Republic, but this information is out there many dozens of times in JavaScript. So here we're creating a text node with our string, and then we're going to sort of apply that to a div that we'll create. All right, so we've got this text node. So we'll just call that text. We can make it a const. Okay. Add some spacing in there. Okay. So the next thing that we'll want is some div. So we'll say even const div window.document.create element, I believe. And this is just a fixed div. And you could absolutely create sort of more complicated abstractions here where you're maybe supplying like the type as a string down into the foreign function call. There's lots of things you can do here. Okay, so we've got the div, we've got the text node, and so the next thing that we'll want to do is append the child. First to the div, and then eventually to the document.body itself. We'll do that in a separate function. So let's say div.append child tx. And then we'll return the div. So we are returning a value. It is an HTML value. It just happens to be this div. Nope. There we go. Okay. So now it's no longer grumpy that we do not have a correct way of doing this foreign function interface. It found the file. And it just matches up the name here. To your export list in this file. Okay, so it happened to find everything it needs, and it trusts that our string to effect HTML is consistent here. I'll often like do a little comment that will even say like what the type is. I'll even do the type signature in the JS, just so that it's clear if you're changing this, then you're breaking a handshake. But that is sort of the most guarantee you can get out of the box. There are also libraries that can help you enforce runtime type safety as well. Okay, so let's go ahead and create that. So I'm just going to say here div is equal to append string to document hello world. I might just rename this because it's really append string to div. We're not adding it to the document just yet. There we go. And it helps if I save my changes in both files. Right. And what we're looking for here is a bind arrow, and just to make the type checker happy, we'll need to use pure unit. So you might be familiar that pure is the same as return. However, you may not be used to seeing unit spelled out. So again, everything has a sort of different value here. In terms of, we're not just using the empty brackets as a symbol like this. It has a name, and in fact, the empty brackets doesn't actually mean unit in Purescript. It means an empty record, you can think of it, or the empty row, so to speak. So it means something distinctly different in Purescript than it does in Haskell, which is why we have this typed type, this written type unit, as opposed to a symbol, and why we have the term level unit as well. For very similar reasons, true and false are also lowercase in Purescript. All right, it's happy at the type checking level. It's just grumpy because we haven't used div yet. So that's going to be our next mission. Is let's take another foreign import, and we'll call this append HTML to body. So this is going to take HTML as an argument, and it's going to have an effect that ultimately returns nothing. Yeah. And now it is once again mad that we have not got the other aspect of the foreign functions fixed. So we need to add another function here. Exports dot append HTML to body equals, we'll just call it HTML. Again, we're creating an effect, so we throw in an extra curried function. And all this is, I think, is going to be window.document. They're fine with just document. I think that should work just fine. So document, it really does exist on the window object, but that's fine. JavaScript can figure that out. And document.append child any HTML that we give it. And we don't need to return anything because we're returning unit. Okay, and then over here, we'll just do the appending. So append HTML to body with the div. That should all type check. It's mad because we're not using log. I will just get rid of log. And whenever you see the owls on PSCID, that means compilation was successful, which means the compilation output was probably picked up by parcel. And so I'm going to take a look and see if we actually have, maybe with a reload, oh, we actually have an error to fix. This is why we might want to have it as an effect. Only one element on document allowed. Oh, we didn't apply it to the body of the document. We only applied it to the document itself. So let's just go in and fix that. Body. And I'm just going to do a rebuild just to make sure it gets picked up. Do a reload. Hey, and we got our hello world on the DOM. So that's kind of a quick overview of working with the DOM from Purescript. I wouldn't necessarily say working with the DOM is something that everyone needs to know about Purescript, but I think that it's a really elegant way of describing foreign function interfaces and just sort of getting a brief idea of how concepts in PureScript might relate to concepts in JavaScript. All right, so that concludes the talk. This should give everyone a pretty good idea of sort of the bare basics of PureScript. I do want to do maybe a follow-up talk. I don't know if it'll be here or elsewhere, but talking about asynchronous work across both languages, JavaScript and PureScript. I'm actually pitching it to PureConf, so I think that's next month. So you might be able to catch me at PureConf as well. All right. Any questions?
Not not so far. People are sharing. People are saying this tutorial is making me happy. Woo! It was really
Cool.
nice, and a really nice hello world also. the standard message.
Yeah, I've realized I have the Zoom chat up. I don't actually have the YouTube chat up.
Oh.
So I may have missed any questions that came up. So
Yeah,
I apologize, but
no questions so far, Ben.
Yeah, I really recommend for anyone who's looking to get started, do take a look at the Spago docs. I think they're kind of one of the best entry points to PureScript. Another great place to look, although it may be slightly out of date and only slightly, is a great book by the actual developer of PureScript itself. The book is called Learn PureScript by Example, and it shows you sort of snippets of PureScript and then the JavaScript and Haskell equivalents. So I think that's really worth a read if you're interested in PureScript. It certainly helped me a lot. One other place I'll direct viewers to is the project Real World Halogen. I'll write it out somewhere, maybe over here. Q to exit. Real World Halogen. Or maybe I'll just bring it up. Real World Halogen is World Halogen is a really, really well documented GitHub project and sort of a book that describes how to build a sort of re-implementation of the Medium blogging platform in PureScript. So you get to see a really principled front-end design using native Halogen component systems that's sort of a similar to React, but built with more type safety for building up a front end in nothing but PureScript. And it uses, I think, monad transformers really effectively, and it's heavily, heavily commented. So I really recommend taking a look here. And if I can find the GitHub, yeah, this is how I learned PureScript, and an awful lot about monad transformers, if I'm honest. So you can go right through the source. So we can go through components, perhaps, and you can see like pretty much every file. You get just a ton of comments. Like just there's almost as many lines of comments telling you what a function does as the actual functions themselves. So if I go to the PureScript, there's a pretty good amount of comments throughout the entire. Let's do like an article list. I don't know. I use this as a pretty great way to learn the system, and he does some pretty amazing things with codexes as well. So setting up sort of type safe page routing for like single page apps, building up real web apps with PureScript. It's a really great resource. All right. I think that's everything I have to say. Any other questions coming from YouTube?
No, Ben. No questions.
All right.
I have a question.
Sure.
You said you're looking for people. Are you looking for people in Canada, or is it like anywhere in the world, or remote, or how does it?
Anywhere in the world. We are
anywhere
a
in the
fully
world.
remote company.
Cool.
We don't have an office anywhere.
Ooh.
Sometimes we get together for fun. But in general, like we have 3 or 4 employees here in Toronto. We have I think close to a dozen employees in the UK. We have people all across mainland Europe and people on every single continent. So
cool.
If you're interested, if you're a Haskeller, like your relative time zone or country is generally not a concern.
Cool. Next question. I have a question. How did you start to learn Haskell? When did you learn it?
Well, I came to it through JavaScript. So in JavaScript, there's a really great YouTube community out there, Function, which focused initially on just functional programming concepts. So that was very helpful to me as a JavaScripter. And they sort of alluded to this Haskell thing that was a mysterious and dark art that might be difficult to learn. And so in a day of frustration, I decided I wanted to learn the least employable thing ever. And so I started learning Haskell, and it really ramped my career up. In fact, I have to say Haskell's extremely employable right now, in a way I did not anticipate.
Okay.
Yeah, so that's my personal story of what brought me to Haskell was actually frustration learning and working with PHP and Solidity and some of these other less than ideal languages, I would say.
Cool. Checking if there's more questions. No more questions. Then thanks again, Ben, for coming. Thank you very much for your talk. And we'll post the link.
Thank you very much for having me.
Yeah, you're welcome. Send over the links you want to post, and we'll dump it below the video once we're done.
Yeah, I'll just, as I stop screen sharing here, I'll jump onto the video myself, and I'll post it in there.
Good.
Great.
So people can find you and find your next talk also at the, what did you say, Pure Conference, or sorry for missing?
Yeah, Pure Conf. I'll drop the link there as well in the
chat,
just once I jump off. Great.
Cool. Thank you very much, Ben.
All right. Thank you. Take care.
Yeah, you're welcome. Thank you very much. Then we're off to the next presentation by Lennart.
All right.
Welcome, Lennart.
Let's see if I can share the right window here. There.
Everything is set up.
Yes. All right. So I'm going to talk about this library that I wrote called Orthotope. I think it's pronounced Orthotope. I don't know. I've never heard anyone say that. I just had to pick a name. So let's get to that slide. According to Wikipedia, an orthotope is like a rectangle, but generalized into n dimensions. So this is because this is arrays that can be n-dimensional, and all the good names were taken, like array and tensor and things like that. So I looked for something with a similar meaning, and so I found orthotope, which I'd never heard of before. It's a terrible name because I can't even remember it myself, but there it is. So so first I should say, if anyone has any questions, please try to interrupt me by posting them in the YouTube chat or something. I'm going to try and keep an eye on it. So first, I should say something about APL, because this is inspired by APL. So APL stands for A Programming Language. So that's a nice, simple name. It's a mostly array-based language. It was designed in the 1960s by Ken Iverson. And I'd say it is way ahead of its time because it's very much a functional language and a mostly sort of immutable data types. It does have variables, but the arrays, you don't really update them, you just create new ones. And if you've heard of APL, you've probably heard of it because it's supposed to be very cryptic, and I'd have to agree with that. So this little program that I've included there computes prime numbers from 1 to R. And yeah, it's fun, but hopefully the Haskell code is not going to be quite as cryptic. I think one reason APL never became popular was that you needed to have a special keyboard to be able to use it, because you can see there are lots of weird symbols in it. And so who has a special keyboard? I don't know. IBM, I guess, because Ken Iverson worked for IBM. I've actually worked on a small machine that IBM made that had this special keyboard, but otherwise it's unusual to see. All right, so Orthotope is, as I said, a Haskell library, and mostly it contains operations that I call structural, so it sort of changes the shape of the array without actually computing anything. So I made this library when I worked at Google, and so it's sort of geared towards the stuff that you want to do when you do machine learning things. So the way you set up neural nets, there's usually a lot of array manipulations, multi-dimensional arrays. And a lot of these structural operations are, maybe surprisingly, constant time. They don't actually do anything to the underlying storage. They just whistle things around in the sort of the array descriptor. I will show some examples of this later on. So I'm going to show you a bunch of examples. That's basically what this talk is going to be. And then I have a few more slides. And thanks to Google for making this open source. I no longer work for Google. I work for Epic Games now, but they have nothing to do with this whatsoever. Epic Games is hiring, by the way, but we're mostly hiring C++ programmers, so it might not be something that this crowd is interested in. So first, I'm going to display arrays in the same way as APL does. This the so here's a sample array. Has rank 2, as it's called. It has 2 dimensions. It's 2 by 3. So 3 is sort of the innermost dimension. It goes horizontally, and then you have a new line and you have the next dimension. So the shape is 2, 3. The rank is 2. The rank is simply the length of the shape. And the size is the number of elements. And so 3, 2 array. So an example of something with shape 3, 1, 2, 3. You can't really distinguish if it has more outer dimensions that have size 1 because they print exactly the same way. But they have different types, so it's important to know if you have something of shape 3 or shape 1, 3. 3, 1, on the other hand, looks different. And as I said, you can have, well, as many dimensions as you like. So here is a 2 by 2 by 3. So first there are, the innermost is 3, and then there's 2, and then there are 2 groups of those 2. Here is another one, 2 by 2 by 1 by 3, as rank 4, another 12 elements. If you see a single thing like a 1, that could be, well, it could have many dimensions. So one is that it could be a 1-dimensional array that has rank 1 and still has size 1. But you could also have arrays that has a shape with no dimensions. That's allowed, and they are often called scalars. So that's sort of the degenerate case of an array. And there is one value in this. You might think that's weird. There are no indices, so how could there be one value in it? But it's the only thing that makes sense. So if you look at the size is always the product of all the numbers in the shape. And so if you take the product of the empty list in Haskell, you're going to get 1. So it makes sense that there is one element in that array. All right, so this library comes in a number of variations depending on how strongly typed you want the API to be. So I'm going to say more about that. I'm going to show the version that is the most strongly typed, where the shape is part of the type. And to do that, you need to turn on a bunch of Haskell extensions so that you can have numerical things in your types, and you can have lists in your types. So here are some sample types. So an array, a 2x3 array of integers has this type, array 2, 3, int. 6-element array, which often called a vector of floats, would be array 6 float. And then here is a 4x4x4x4 array of booleans. So it's nothing strange about this, except that you can have these numeric types. So if you haven't seen that stuff in Haskell, this might look mysterious, but you need to turn on some extensions like data kinds, and then you can have these kind of types. And if you have a proper dependently typed language, then these would be sort of the same kind of numbers as the one you compute with, whereas in Haskell, these numbers are type level numbers, which are very different from the object level numbers. All right, so now I'm going to switch to my terminal window instead. So instead of showing you slides, I can type in some window. There is, that seems to be working. Okay, so let's have some simple examples. I hope this is large enough so people can read it. Let's make an array. The easiest way to make an array, or one easy way, is to say from list, where you can give it a bunch of numbers. And well, from list has no idea what the shape of the array should be. So you really need to put a type on it if you're going to get anything out of it. Otherwise you get some error message that it can't figure out what it's going to be. So the PP is just a function I have for pretty printing things. So pretty printing A gives you this 1, 2, 3, 4, 5, 6. If you just look at A without pretty printing, it kind of shows you how it was built. If you type this back in, you will get the same array. So if we look at the type of from list, you can see that it takes a list of elements and gives you an array back. And the first argument to the array type constructor has to be a shape. Okay, so it's kind of tedious to give the type this way all the time. So instead, you could say instead A equals from list, and you have to have another extension on Haskell turned on where you can actually give it type arguments. So the shape is the first type variable in if you look at the quantified type for from list. So you can give that explicitly and then say 1 through, well, let's 1 through 6. And now if we look at that, we get exactly the same array. And this is the way I will usually write things with explicit type application. You have to use that a lot if you use this library and have the sort of the strongly typed version of it. And if we look at the shape, well, it's 2 by 3 as expected. The rank is 2. The rank, remember, is the number of dimensions. So it's the length of the shape. So that's 2. And size of A is the number of elements, which is 6. Another nice way of making arrays it comes from APL. It's this function called iota because it was written in APL with the Greek letter iota. And it gives you all the numbers from 0 up to this 1 minus 1. All right. Any questions? No, I'm surprised. I hope the question stuff is working. Well, so what can we do with an array? Well, so something typical we can do with an array is to index into it. So let's do that. There's a function called index. We should pretty print the result. So you give it a single index, and that means you will index into the outermost dimension of it. And the outermost dimension is the sort of 1, 2, 3, or 4, 5, 6. So now I picked 1, 2, 3. Oh, sorry, I picked 4, 5, 6. If I index by 0, I get 1, 2, 3. And then I can, of course, since that's an array, I can index into that again. And then I get 4. And if we look at what is the type of this one I've indexed twice, well, it's still an array, but it's one of these scalars. So it's an array with no dimensions. So if we just showed this thing, it would show like that. But if we pretty print it, it looks nice. If you absolutely want to leave the wonderful world of arrays and get back to normal numbers, there is a function called unscalar that takes a scalar thing and gives you back the actual number in it, or whatever it is. It doesn't have to be a number. And if we look at the type of unscalar, we can see that, yes, it only takes one of these 0-dimensional arrays and gives you back the A. So yes, indexing, not very exciting. Next one is not going to be very exciting either. So here's our A. There is a transpose function. And if you're doing any matrix algebra, you think of transpose as just flipping the two axes. But these arrays can have an arbitrary number of dimensions. So there is no meaningful transpose that doesn't also need to know how to transpose it. So we need to say, okay, this has two axes. How do we want these two axes to be permuted? So if we say the 0th dimension should go map to 1 and the next one should map to 0. So this will be ordinary transpose. If we do the permutation is just 0, 1, then nothing happens. So for just 2-dimensional arrays, this is sort of a bit nonsensical, but if you have multi-dimensional arrays, you need to give this permutation. Then you might wonder what would happen if you, well, I don't know, make a mistake here. Then you get a horrible error message that says that, well, you used transpose in some weird way. There is no dimension number with index 2. You have the 0 and 1. I see someone ask me here if I considered naming it an array library. Yes, I did actually consider naming it array, but I don't, yeah, that name is sort of means so many things in Haskell already, so I wanted to have a more unique name, but it might have been a better idea. All right, let's just do another little transpose here. So let's make a different B. Make a 3-dimensional array here. Well, I could just make a mistake here, and so you can see what happens. So from list is of course impossible to have any strong typing of, because you don't know what the length of the list is. So you you will just get the runtime exception saying size mismatch. But if we do the correct ones, so here is the array. So there are 2 blocks, that's the outermost one. Then there are 3 rows in each of those blocks, and each of those has 4 items. So now you could, for instance, well, there are many ways you could transpose this. I don't know, 2, 1, 0. Which, well, I won't go through looking at this, but I mean, you can see it has the innermost dimension is now the one that was outermost before. So 1 and 13, and then 2 and 14, and so on. So now you can see why you really need to give it some kind of permutation here rather than just saying transpose. You might wonder what the type of transpose is. You don't really want to see it. It's some bizarro type using all kinds of type level programming features of Haskell. But transpose will check that what you're giving it is right, otherwise you'll get a type error. All right, so here we have A again. Another thing you might do with your arrays is to what is called a reshape, which is written by the Greek character rho in APL. So I could reshape this into a 3x2 array. So this doesn't do the same as transpose. This just says keep the elements in exactly the same order as you had before, just interpret them as being a 3x2 array instead. So it's still 1, 2, 3, 4, 5, 6. Or you might say, oh, give me, oops, Haskell quirk. 6-element array, or you can have a 6x1, and so on. And here's a somewhat nice thing about type inference. So I'm going to reshape iota into a 3x3x3. If you remember when I showed iota before, I gave it a type level argument saying how many things I wanted it to produce. So I need 27 things here, 3x3x3. But I don't have to say that because the type checker can figure out that, yeah, 3 times 3 times 3 is 27. So it must be iota 27 here for it to make sense. So sometimes you don't have to give these type level arguments because the type checker can't figure out what they're supposed to be. What's the type of reshape? Well, that almost makes sense. Takes an array of some shape into an array of some other shapes. They have to be shapes. And here it's expanded something. The size of the shape and the size of shape prime should be the same. That's what that's saying. All right, let's make a different B here. So it's a 2x3x1. So the innermost dimension is 1. So there's only 1 element per row here. So another fairly common thing you want to do is that you want to sort of duplicate some elements along some axis. So there is an operation called stretch, and you tell it how you want to stretch it. And so you can only stretch dimensions that are of size 1. So this says 2, 3, 1, and I want to stretch that to 2, 3, 5, which means you'll get 5 elements along each of these instead of 1. Okay, there was a number of boring sort of structural operations. You can do other things. Like you can add them, and you can add 1. You can have other numbers than 1, 2, 3, 4, 5, 6 in your array. It's just that I've used that in all the examples. Let's make another little thing here. Okay, so this is 2 elements, 100 and 1000. So now I want to add these two C to A, but I want to sort of replicate the 100 along the innermost dimension and the 1000 along the other dimension. So there's an operation called broadcast that can do these kind of things. That did not work. C. So broadcast again has some type level argument here that says, okay, the dimensions that C has, where are they going to end up when we broadcast? So broadcasts increases the number of dimensions you have because it needs to be a 2 by 3 after you've done the broadcast. And this is saying, okay, the dimension that I have here, that should end up as dimension 0. So you can do all these kind of broadcasting things if you have, say, a vector and an array, and you need to add them. They can be slightly fiddly. So some APL does a lot of these broadcasts automatically, but it always, some of them work without writing anything. So this one I think would have done the right thing in APL if you just say A plus C. But there are often choices which dimension you want to broadcast. So one of them will be the default one, and that works easily. And if you don't want that one, then you have to write something more complicated. So I decided you have to write the complicated thing all the time in Haskell. All right, so let's see. Okay, so let's do another. Look at A, just so we remember what that looks like. So there is something that is like the fold operation in Haskell, kind of like fold. APL calls it reduce, so I call it that too. So it takes a function, what to do between all the elements and how to start it, and then some array. And so this added up all the element 1, 2, 3, 4, 5, 6. If you add those, you get 21. But it might not be exactly what you thought, because it didn't return a scalar. It didn't return an int, or it returns a new array, a scalar array that has 21 in it. So if we look at the type of reduce, it has an unusually simple type. Takes this element-wise thing and how to start, and an array of any shape, and it will do this operation between all the elements and give you an array that has the result in it. So you might wonder, why do you want the result to be an array? Well, we'll see here in just a second how this can be useful. So let me first define this function, so I don't have to type so much. So sum stat function. So this did reduction of the whole array. What if I didn't want that? What if I say wanted to only sum the elements of every row? So I want to add up 1, 2, and 3 and get 6, and I want to add up 4, 5, and 6 and get 15. Well, like APL, there is something called re-ranking. So what does this do? Well, it says, take the array A, and this number here, 1, says, go 1 level into it, and then apply sum to all those subarrays. So 1 level in, you have 1, 2, 3, and you have 4, 5, 6. It will apply sum to those, and that sum sort of replaces the things that you added up. And so you're still left with 1 dimension, because you went 1 dimension in, so the outermost is still there, which then has 6 and 15 in it. Okay, so that's fair enough. What if I had wanted to add up columns instead of rows? I mean, rows, that's fine, but columns is also good. Well, the way you do it in this library is that, well, you have to first make them into the rows then, so you can use a transpose. So first you flip the 2 axes of A, and then you go 1 level into that, and you add those, and then you get 1 plus 4, 2 plus 7, 3 plus 6. And do I have my B here still? No, it's a boring B. B equals from list. And you can, of course, go more than 1 level down when you do your re-ranking. So this says, look 2 levels into the array B, and then apply sum to those subarrays. So it will add up 1, 2, 3, 4, and you get 10, and 5, 6, 7, 8, you get 26, and so on. So given re-ranking and transposition, you can kind of take your, if you have some function that goes from arrays to arrays, you can make it perform this operation on any sort of sub array, or sort of any of the axes that you want. You need to transpose to get the axis in the right place, and then you need to re-rank to get it to apply to the correct subpart of the array. So I'm going to do a matrix multiply, but just to remind you what that looks like, I'm going to need to share the other screen again because I have a slide. So if you don't remember matrix multiply, let me give you a little reminder. So you have two matrices. So I have my favorite examples here: 1, 2, 3, 4, 5. Oh, 5, 5. Well, it's oops, that's just 5, 6. It should have said. Why change a winning strategy? So to produce this element in the output, you take sort of the first row of this matrix, first column of the second one, and you multiply them element-wise together and add it up. So that's the dot product of the two. So 1 times 11, 2 times 13, 3 times 15, you get 82. To get the next element, you take the first row, you can take the second column, and you do the same thing, and you get 88, and so on. So let's see how we can do that and with the operations that we have. So let me switch back to terminal again. Right. So let me make the same B as we had. So A, we have the same old one, but let me make a B that is the same as I showed on that slide. From list, so it needs to be 3 by 2, and it had 11 through 16 in it. So that's the one we had. And so one of the first things we need to do is to transpose this one. So so that's, you could probably guess what that looked like. So let me show you the idea of this. So we're going to broadcast both A and B, but in slightly different way, so they can be combined to achieve all these products that we need. So let me give this a name, AS. We're going to broadcast. A, and since I need to give it lots of types here, since I'm doing it, the type checker doesn't know how I'm going to use it, so it needs some help. If you write it in one big function, it's much less types in here. So now I broadcast this dimension, so we get blocks of 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6, 4, 5, 6. And then we're going to do a similar thing with the transposed B. So BS will be broadcast. But now we're broadcasting slightly differently. This also needs to be an array, 2 by 2 by 3. So this has been broadcast. This doesn't look right. Oops, AS was wrong. Sorry. There's AS, as it should be, and BS. So you can see that AS has broadcast things so that there are two duplicates of this here, whereas this has this block duplicated over here. So if we now just take these two and multiply them together, then we get all these products of elements that if we sum them now, if we sum every row, those will be the 4 elements that is the result of the matrix multiply. So let's do that. And there is the result. And there is, of course, no looping or anything in sight. We just take the matrix and reshape them in different ways and combine them with sort of array-sized operations and get the result. Okay, I'm going to switch back to the slides again. So if you combine these things together that I just typed into a function, called it MM here, it will have this type. And so you can see, if you ignore all the constraints here, you see that it takes an array of m times n and an array of n times o and gives you an array of m times o. So the inner sort of the second dimension here and the first here, is the one we're summing across. So that one disappears. And this is the same as I did before, but just with little less type annotations on it. So AS, you broadcast the A, BS, broadcast the transpose, re-rank, adding up the elements, and that's it. Now, if you actually want to do matrix multiply, you shouldn't do this because the Orthotope library also comes with an interface to the H matrix Haskell library, which uses BLAS and LAPACK, which is written in, well, depending on what platform you run on, it might be written in Fortran, it might be written in C, but it's very fast matrix multiply. So this was more to illustrate how you can do things in Orthotope. So a few words about implementation. So all these operations that I did, like transposing and stretching and broadcasting and so on, they are not expensive. In fact, they are all constant time operations because they never touch the actual elements. And this is an idea that dates back to the 60s too. The IBM called them dope vectors. So this is, an array has some piece of storage and some kind of descriptor of what the array is, and that's what's called a dope vector. And if you want to be mathematical about it, so any affine transformation on the index space can be done in this and done in constant time. And I've written the complexity. So transposing, windowing for if you want to do convolutions, slicing, reversing, indexing, striding where you skip elements, they are all constant time. Reshape, re-rank, they might be constant time. It depends a bit on what you've done before. And of course, the thing that has to do sort of computation and touch all the elements, you have no choice but having them be linear time, or worse than linear if you doing something complicated. So before I talk a little bit of implementation, I'm just going to mention all the variations that are of this library, unfortunately. So there are 3 levels of types. So I've shown you the ones that's called shaped, where the shape of the array is actually part of the type. So an array 3,2 int is a 3x2 array. Slightly less strongly typed, they're called the ranked. Then it's only the rank, so you only know the number of dimensions. So array 2 int says there are 2 dimensions, but the actual size of the dimensions is only known at runtime. So you can't check that at compile time. And dynamic, which has no shape information at all. So array int says, well, it's an array of int. I have no idea what the shape is at compile time. That's all runtime information. And of course, the ones that where you have runtime information about the shape, they do the checks at runtime and they will just throw an error if the shapes don't match properly. So unfortunately, the APIs have to be slightly different, but I've tried to make them as similar as possible. So for instance, the from list, if you have the shaped one, you pass in a type argument that says, I want to make a 3x2 array. In the dynamic one, well, it's a runtime thing. So you pass in an ordinary list that says 3x2. I want to make a 3x2 array. So if you have one of these, a shaped or a dynamic or a ranked, converting between them is very cheap. Is only, well, from stronger type to weaker type, there's nothing to do at all. The other direction, you have to do a little dimension check. So that's one variation. Sadly, there is another variation. So if you want to do efficient manipulation of arrays, you need them to be unboxed. So for instance, the efficient Fortran implementation or whatever of matrix multiply, they need to be unboxed arrays of things. And so there are 4 variations of this library, depending on what kind of boxing you're going to be. So things can be boxed. Then the underlying storage that it uses for the array comes from data.vector, which is a nice efficient vector library for Haskell. Boxed vectors, so all the elements are boxed. They can be unboxed from data.vector unboxed. These 2 libraries have exactly the same API. It's just that there are some constraints. You can't unbox anything. You can only unbox certain things, for instance, numbers. Even more constrained is the one that's called storable, which again has the same API, and it's again unboxed things. You have like unboxed numbers, but now the actual storage is actually pinned in memory, so it is at a fixed address. The garbage collector cannot move it, and that's so that you can call into C code or whatever with this, because you can't have the garbage collector move things around. It has to have a fixed address. And then there is a 4th version of it where you can decide what kind of storage. So it's sort of polymorphic in the storage. You can provide whatever you like. Which means there are 4 versions of this sort of the storage stuff, and there are 3 versions of the type level, which means there are actually 12 different modules you have to pick from that all have kind of the same API, but gives you slightly different things. And it's sad that there has to be 12 things, because the code for them are pretty much the same. Not quite, with the different typing. So I regard this as a sort of flaw of the abstraction power in Haskell, especially this storage one. It should be possible to be polymorphic in your boxedness. And I think these things are coming to Haskell. There's this new thing called levity polymorphism that might be able to do that. Okay, so some words about implementation. What does it look like? Well, so for an array, for each of the dimension, you know what size it has. So if it's a 2 by 3 array, the sizes are 2 and 3. Then there's something called the step size, that tells you if you need to get from one element to the next element, how much do you need to step in this vector? So this vector stores the actual elements. And this tells you to get from one element to the next, how much do I have to move in the vector? And then there's also an initial offset into the vector. And so if you have some indices you need to index by I1, I2, I3, then you can find that element in this vector by taking the first index times the first size, the step, second index times the second step, and so on. And you add the offset, and that will be the position in the vector. So to show a couple of examples, here is the 1, 2, 3, 4, 5, 6 array again. So sizes are 2 and 3, and the steps, well, if you're on the outermost dimension, the one with size 2, if you want to move from 1 to 4, you need to add 3. So that step is 3. You need to add 3 here in the vector, and the offset is 0. I mean, you could have a bigger thing. So if you take a slice, the offset might not be 0. So for the most strongly typed where the size, the shape is part of the type, you don't actually need to store the sizes because they're part of the type, so they are known by the compiler. But for the other ones, the ranked and the dynamic, it's actually part of the storage that you have for your array, that what size the sizes are. Here's a slightly different example. So here's a 3 by 4 matrix that is full of 7s. Well, you can represent that with a vector that has only a 7 in it, and size is 3 by 4, and it says to get from one element to the next one, you step by 0. Because, well, they're all there. If you don't move around, you get 7 every time. And that's how, sort of, when you do this stretch operation, that it doesn't duplicate any storage. It just sets one of the steps to 0. So it's saying that if you're moving in this time along this dimension, you don't need to move at all. Here is an example of a transpose. So you have 1, 2, 3, 4. It's this array here. What do you do when you transpose it? Just the transpose 1,0 that we had. You just need to swap the sizes and you swap the steps. Oops, it's not supposed to say offset 1 here. It's supposed to say 0. I'm sorry. So that's wrong. The offset should be 0. No need to move any kind of data around here. You're just saying, yeah, well, for the outermost dimension, you now need to step by 1, because to get from 1 to 2 here, you step by 1. And then the innermost dimension, you need to move by 3, 1 to 4. Too much copy and paste. Here's another example. If you take a slice of an array, so here's a 2 by 3 matrix. Again, same one. If you take this 2 by 2 slice that has 2, 3, 5, 6, what you need to do, well, you don't need to do much. You change the size to be the correct one. You leave all the steps alone, and you just change the offset, saying that, well, we start at 2 now. So to get from 2 to 3, it's the innermost dimension, you move by step 1. If you want to get from 2 to 5, well, you move by step 3. So 2, 1, 2, 3, you get to 5. And so didn't need to touch anything except this stuff here in the thing that's often called a dope vector. So this way of implementing arrays was done in APL also a long time ago, probably 60s, at least early 70s. So that's all I had to say. If you want to try it out, you can download it from Hackage. And there's sort of an accompanying package that has the fast matrix multiply. And once you have matrix multiply, and you can also implement convolutions fairly easily. This second package here also has an implementation of convolutions. If you have matrix multiply and convolutions and all these sort of structural operations, you have basically everything you need to implement neural nets and do some machine learning experiments, which is why I implemented this in the first place. All right, that's all I had, and I see no questions, sadly. I really dislike giving talks this way. It's so much nicer to be able to look people in the face and force someone to have a question.
Yeah, I agree, Lennart. It's much easier to have like a discussion with people when you're face to face.
Yeah.
Could be talk out in the void in a sense.
Yes, it's hard to know if anyone's listening.
Yes, exactly. I have a question.
Yep.
I don't see any questions, so I'll just shoot away my questions. Has this been used in any live application for ML or neural nets?
No.
Or it's been used in experimental ways, or?
So yeah, so we used it in experimental ways at Google, so to sort of verify some stuff that a compiler we had for a machine learning chip that I was part of developing. Unfortunately, they closed down the project when it was almost done. The pandemic came, and the CFO of Google said, "Oh, we need to save money now because the pandemic is going to be terrible for Google. So let's shut down some projects." So they did that. And then it turned out Google made more money than ever during the pandemic.
It was just the inverse of what the CFO thought.
Yeah.
Yeah. Yes, let's see if no more questions. Are you coding Haskell today, or are you coding C++ at Epic?
No, I'm doing Haskell, but it's, well, we just hired Simon Peyton-Jones as well. So we are the only two Haskellers at Epic.
Currently, but soon you're 3, so you're 50% growth. Or yes. Did we lose Lennart? Yeah. No.
Well, I think things froze up here. So if you said anything, I missed it.
Oh yeah, we thought we lost you, but you're back. I said, like, if you hire one more, the growth is 50% of Haskellers in Epic.
Yeah. So Tim Sweeney, who still owns the majority of Epic, is very interested in programming languages. He's a programming language nerd. So he gave some talks way back in like 2008 at Popple about some ideal language that he'd like to have. So he's been tinkering with a programming language for the last 20 years.
Oh.
And so, I mean, now he has a lot of money, so now he can afford to hire some programming language people.
Yes, and just try out stuff for fun.
Yeah.
Or for experiment and see where you can go with
it. I mean, there will be some new language for the Unreal Engine in the near future. That's all I can say.
Cool. We're looking forward to that. Yes. Don't see any more questions. However, a lot of people thanking you for a great presentation. So again, thanks.
Thank you. Thank you for listening.
Yeah, thank you. It's very interesting. It was a long time ago. I mean, I read mathematics in university, I think 15 years ago, and then we did this like a lot of array operations. And also,
Yeah, I mean, I hadn't done anything like that until I started doing some machine learning stuff. But then you have to brush off all your linear algebra things.
exactly. Exactly. Yes. Thank you again, Lennart, and thanks for your presentation. Then I'll
Thank you.
yeah, you're welcome. Then I'll wrap up the evening. First up, thanks all the presenters, Lennart and Ben, for coming and presenting. Thank you very much, and thanks for all the viewers and watchers. Thank you also very much. We are back on the 15th of February again at 8 o'clock. We have one presenter ready, and we're looking for the next one. So if you want to present, please reach out to me over LinkedIn, Twitter, wherever you want to reach out to me. If you find the contact details either here in YouTube or in the meetup page. Yes, and please remember, if you want to support the community, please remember to subscribe and go over to the meetup community and join us there also. Again, thank you for watching tonight, and have a nice evening, everyone. Bye bye.